A stone wall can outlast an empire and laugh in the face of earthquakes. For over 1,000 years, ancient structures in the Andes have done exactly that, standing firm in one of the most violently shaken places on Earth. This was no accident, but the product of a forgotten science. By the end of this exploration, you will understand the precise engineering secrets that allowed these monuments to dance with seismic waves instead of crumbling before them. How did builders without modern tools create walls that modern analysis struggles to fully explain? And what hidden design rules turned immense stones into a flexible, living fabric? In a world of increasing instability, what can these silent stones teach us about building a lasting future? This landscape is not a passive backdrop, but an active, shaping force. The Andes themselves are a monument to movement, a mountain range still being pushed skyward by the slow, grinding collision of continental plates. Picture the immense Pacific Ocean floor, the Nazca Plate, being forced downward into the Earth's molten mantle. This relentless subduction does not happen smoothly. It is a stick-slip process where unimaginable pressure builds until it is released in a violent shudder that travels through the very bedrock. For the cultures that called these slopes home, the ground was not a symbol of stability, but a living entity with a volatile temper. Their world was one where the horizon could literally ripple, and a deep, groaning roar from beneath the soil was a familiar, terrifying sound. This was not a rare catastrophe, but a frequent and expected visitor. To build a civilization here was to accept a fundamental truth, that anything you constructed would one day be tested by the Earth's own furious energy. This constant, looming threat did not lead to simpler, temporary buildings out of fear. Instead, it sparked a profound architectural revolution. Over countless generations, through observation and heartbreaking loss, these cultures began to decipher the language of the quakes. They learned that rigid, brittle structures fought the movement and were shattered for their defiance. The solution, then, was not to resist the Earth's power, but to find a way to join its dance. This hard-won wisdom, born from millennia of living in the planet's most active seismic workshop, became the invisible blueprint for every stone they would lay. The genius of their approach lies in a fundamental rethinking of the relationship between a building and the ground, where we often seek to anchor a structure into an unyielding foundation. They designed for a foundation that would yield. This first principle was not about creating a fortress, but a partner to the Earth's motion. Modern rigid frame buildings, with their deep concrete pilings and welded steel skeletons, are engineered for immense vertical strength. But when a seismic wave hits, that very rigidity becomes a liability. The structure tries to hold its ground, fighting the movement, and the resulting stress concentrates at its weakest points. The outcome is often a sudden, catastrophic failure, as the building is literally shaken apart from the inside. The ancient Andean engineers observed this brutal truth through generations of loss, and they arrived at a radically different solution. They asked not how to make a wall strong enough to resist the quake, but how to make it clever enough to survive it. Their goal was to design a structure that could absorb the terrifying energy of a tremor and safely dissipate it, like a deep breath released after a shock. This required a building to be flexible, to have a controlled ability to sway and settle back into place without fracturing its own bones. This principle of dynamic accommodation became the invisible blueprint, the bedrock philosophy guiding every cut of stone and every choice of mortar. You can see it in the very fabric of their walls. They avoided creating single, monolithic slabs of masonry. Instead, they built up their structures as intricate assemblies of individual stones, each one carefully shaped and positioned. During a tremor, these stones are not locked in a death grip with their neighbors. they are designed to micro-shift, to rock and settle against one another in a complex, energy-absorbing dance. This disperses the force across the entire wall, preventing any single point from bearing the full, destructive load. It is a stunning anticipation of a concept we now call base isolation, where modern buildings are placed on flexible bearings or sliders to decouple them from ground shaking. The ancient builders achieved a similar effect centuries before the physics was formally understood, and it all began with their most critical and often overlooked innovation, the preparation of the very ground upon which everything else would stand. Their strategy required a perfect partner in the ground itself. This is where the invisible work began, a deep and deliberate conversation with the earth that started far below the surface. Before the iconic stones ever touched one another, Andean engineers would engage in a process of profound preparation. They did not simply clear a patch of land and start building. Instead, they would often excavate, digging down through layers of loose soil and sediment until they reached the unshakable solidity of the bedrock. Imagine the labor involved, moving tons of earth by hand, all for a foundation no one would ever see. In other instances, for sites where bedrock was too deep, they constructed massive trenches, which they then filled with a carefully selected mix of stones and compacted gravel. This created an artificial platform of exceptional stability. The purpose was twofold. First, it prevented differential settlement, ensuring the massive wall above would not crack under its own weight as the softer ground beneath it naturally shifted over time. But second, and more critically for seismic survival, it created a unified base. This deep foundation acted like a raft, a single, coherent platform that could carry the entire structure. When an earthquake's waves rippled through the ground, this prepared base helped ensure the wall moved as one solid piece with the motion of the earth below it. The goal was to avoid having different sections of the foundation lurch in opposite directions, which would instantly tear any wall apart. They were, in essence, giving the earth a firm hand to hold, so that when the shaking began, the building and the ground were partners in the same motion. This principle extended beyond flat ground. On the steep slopes so common in the Andes, they sculpted the land itself into a series of broad, level terraces, held in place by immense retaining walls. These were not just agricultural steps, they were a masterclass in geotechnical engineering. By cutting into the hillside and creating these stable platforms, they prevented the entire slope from collapsing in a landslide during the intense vibrations of a quake. The foundation was never an afterthought. It was the first and most critical component of the seismic defense system. It was the deep root system that allowed the tree to sway without toppling. All of the intricate stonework above, the interlocking puzzles and precise angles, would be meaningless without this hidden, unifying base. It set the stage, creating a stable canvas upon which the true artistry of flexibility could be performed. And that artistry is most perfectly expressed in one iconic technique, a stone fitting method so precise it seems to defy the tools of its time. This intricate stonework represents a seismic defense system carved in granite. The most visually arresting examples are the polygonal walls, where massive, irregularly shaped stones fit together with a precision that seems to defy the era's tools. These are not simple stacked blocks, but a colossal, three-dimensional puzzle assembled without mortar. To the modern eye, it looks like artistry, and it is, but every angled cut and curved seam serves a profound engineering purpose. This technique is a seismic masterstroke. During an earthquake, the ground does not shake in a uniform back-and-forth motion. It jolts, twists, and rolls in complex waves. A rigid, mortared wall would try to resist this movement as a single, brittle unit, and it would fail. A polygonal wall, however, behaves completely differently. Each uniquely shaped stone is locked in place by the geometry of its neighbors, but it is not fused to them. When the tremor hits, these stones can shift and rotate minutely within their interlocking joints. They rock and settle against one another. The incredible energy of the quake is not concentrated into a few catastrophic stress points. Instead, it is dissipated as friction across the countless contact surfaces between the stones. It is converted into the gentle grinding of granite on granite, a safe release of force that prevents any single crack from forming and spreading. Here, the very irregularity of the stones is their greatest strength. In a wall of uniform, rectangular blocks, the straight mortar lines between them create perfect lines of weakness. A seismic wave can travel along these lines like a zipper, tearing the wall apart. In a polygonal wall, there are no such straight paths. A crack starting in one stone immediately runs into the interlocking shape of its neighbor, which deflects and disperses the energy. The wall becomes a flexible, monolithic fabric, a stone tapestry that can ripple and sway without unraveling. This is not a loose pile of rocks. It is a coherent, intelligent structure where every irregularity is a calculated part of the whole, a permanent answer written in stone to a question the earth asks again and again. The true secret lies not in the stones themselves, but in the spaces between them. Look closely at one of these polygonal walls, and you will see a design that appears beautifully chaotic, a random mosaic of giant shapes. Yet this was an illusion of profound intelligence. Every angled face, every subtle curve was carved with a singular purpose: to create multi-directional interlocking. This means each individual stone is not just held by the one above and below it, as in a simple stacked wall. Instead, it is locked in place by 3, 4, or even 5 of its neighbors, each pressing against it from a completely different angle. Imagine a single piece in a 3-dimensional puzzle, gripped on all sides by the unique contours of the pieces surrounding it. This intricate confinement creates a living network of compressive forces, a silent conversation of pressure and counterpressure that holds the entire assembly together through sheer geometry. When the earth begins to shake, this network comes alive in a dynamic redistribution of energy. The forces traveling through the wall do not follow a single, vulnerable path. They flow through the web of contact points, shifting and dispersing across the entire structure. This is the core of its resilience. There is no central keystone, no single, critical point of failure. In a classic arched doorway, the removal of the central keystone causes the entire arch to collapse. Here, that vulnerability is engineered out of existence. The load is shared communally, borne by the collective strength of the whole assembly. If one joint experiences minor movement or even a tiny fracture during a quake, the force simply finds another route through the network. The integrity of the wall does not depend on the perfection of any one connection, but on the resilient redundancy of all of them. It is a lesson in distributed strength, a stone-built version of the old saying that a chain is only as strong as its weakest link, except here, the builders created a structure with no weak links, only a flexible, interwoven web. This system operates much like a spider's web, which can absorb the impact of a falling leaf because the tension is distributed across countless silken threads. In the wall, seismic energy becomes that leaf, and the intricate joints are the threads that catch and dissipate its force, allowing the whole to tremble, to adjust, and to settle back into place, forever changed yet eternally whole. Even the slightest inward tilt of these walls is a deliberate act of genius. Stand before one, and you might sense it leaning toward you, a subtle invitation that is actually a profound statement of stability. This gentle batter or taper is not a construction error or a sign of age. It is a calculated design feature that fundamentally transforms how the wall interacts with gravity and seismic force. A perfectly vertical wall has a high center of mass, and when shaken, it can topple like a tall bookcase. By tilting the entire structure inward, the builders dramatically lowered its center of gravity, creating a form that inherently wants to settle back into itself, not fall outward. This transforms the wall's profile from a simple rectangle into a trapezoid, a shape celebrated in engineering for its superior resistance to overturning. The real magic, however, happens during an earthquake. As the ground lurches, the inward tilt uses the wall's own immense weight as a stabilizing force. The shaking motion actually drives the stones further into their inclined planes, tightening the entire assembly in a gravitational lock. It is a self-correcting system where the energy of the quake is harnessed to make the wall momentarily stronger, compressing the joints instead of pulling them apart. This principle of inclined stability extends to every single opening in the structure. Look at any doorway, window, or ceremonial niche in these ancient sites, and you will never find a perfect rectangle or a sharp 90-degree corner. Every opening is a trapezoid, wider at the bottom and narrowing toward the top. This is not merely an aesthetic choice, it is a direct application of seismic wisdom. In a rectangular opening, the corners are points of extreme stress concentration during shaking, like the weak spots on a piece of paper you are about to tear. A seismic wave hitting that right-angled corner can easily initiate a crack that will race upward, splitting the wall. The trapezoidal shape elegantly eliminates this vulnerability. By sloping the sides inward, the forces are guided downward along the angled faces and safely channeled into the solid mass of the wall at its widest, strongest point. There are no fragile corners to fail, only continuous, supportive slopes. This holistic approach reveals a design philosophy where every single element, from the grand sweep of a fortress wall to the shape of a humble window, was conceived as part of an integrated seismic defense system. The geometry itself became a language of survival, speaking in slopes and angles that conversed directly with the forces of the earth. The choice of stone itself was a critical layer of their seismic defense. These builders were not merely selecting rocks for their size or appearance, they were acting as master geologists, reading the landscape for materials with the right physical character. For the most crucial, load-bearing elements of their walls, they consistently sought out dense, hard stones like andesite or granite. These igneous rocks, forged in volcanic fire and cooled over eons, possess a granular, interlocking crystal structure that gives them tremendous compressive strength. They can bear immense weight without crushing, a fundamental requirement for any structure meant to last centuries, but strength alone was not enough. The true artistry and the secret to the wall's flexibility lay in what they did to these stones next. The shaping process was an act of profound patience and precision. Using stone hammers and abrasive sand, workers would painstakingly grind two stones against each other for hours, perhaps even days. The goal was not to create two perfectly flat, mirror-smooth faces. That would have been a mistake. Instead, the aim was to achieve a complementary fit, where the subtle convex curve of one stone met the perfectly matched concavity of its neighbor. Think of it not like placing two sheets of glass together, but like clasping your own hands, where the ridges of your fingers nestle into the spaces between the knuckles of the other hand. This intimate, three-dimensional contact maximizes the surface area where the stones touch. More surface area means dramatically increased friction, the force that holds them together and resists sliding during a quake. This deliberate avoidance of flat planes is a brilliant insight into their understanding of physics. A completely flat interface between two stones under seismic shaking can behave like two slick pieces of ice, sliding past one another once the friction is overcome. The ancient masons engineered that weakness out of existence by leaving intentional, subtle undulations, small bumps and dips across the contact surface. They created what are essentially natural keys. These miniature topographical features interlock at a microscopic level, mechanically resisting any lateral shift. During an earthquake, as forces try to push the stones sideways, these tiny keys engage, converting a simple sliding motion into a complex struggle against interlocking geometry. The energy required to make the stones move past each other becomes far greater, allowing the wall to hold firm through tremors that would shatter a mortared, flat joint. It was a marriage of material science and meticulous craftsmanship, where every hammer stroke was a conversation with the stone, asking it not just to be strong, but to become a cooperative part of a greater, living whole. Perhaps the most radical departure from conventional building is what they chose to leave out entirely. These iconic walls stand without a single drop of binding mortar between their stones. This was not a shortcut or a sign of primitive technique. It was the very heart of their seismic genius. In most ancient and even many modern structures, mortar acts as a glue, fusing individual blocks into a single, rigid mass. But in an earthquake zone, that rigidity is a fatal flaw. Historical mortars, often made from lime or clay, are brittle. When subjected to the intense shearing and twisting forces of a tremor, they can powder and crumble, disintegrating the very bonds that hold the wall together. Once that glue fails, the stones become a deadly, collapsing pile. The Andean builders understood this vulnerability on an intuitive level, and they engineered a stunningly elegant solution. They removed the weak link. By foregoing mortar completely, they forced their structures to rely on a far more resilient and dynamic binding force, the pure, powerful physics of friction. The immense weight of the stones, combined with their exquisitely carved, interlocking faces, creates tremendous pressure at every point of contact. This pressure generates kinetic friction, the same force that lets you walk without slipping on a sidewalk. In their walls, friction becomes the silent, omnipresent guardian. During an earthquake, as the stones are compelled to shift and grind against one another, this friction does not vanish, it transforms. It becomes the system's primary energy absorber. The terrifying lateral force of the seismic wave is not fighting against brittle glue, it is fighting against the immense, grinding resistance of granite on granite. A tremendous amount of that destructive energy is converted into harmless heat and sound right at the microscopic interfaces between the stones. Some researchers have even theorized that during a major tremor, these walls would not scream with the sound of cracking stone, but emit a deep, low rumbling, a resonant hum of countless stones dancing in friction's embrace. This allows for something modern engineers strive to achieve: reversible deformation. Imagine pushing gently on a flexible sapling. It bends, and when you release it, it springs back to its original shape. The mortarless wall operates on a similar principle, but on a monumental scale. It can sway, its stones can rock and settle into new, temporary positions under the force of the quake. Yet because nothing is permanently glued or fractured, once the shaking stops, gravity and friction guide the stones back to a stable, nearly original configuration. The wall breathes, moves, and settles. It is an early, breathtaking manifestation of what we now call elastic design, the ability of a structure to withstand deformation without permanent damage. In their silent, mortarless joints, these ancient builders encoded a lesson that still resonates: that sometimes the strongest bond is not one that holds things perfectly still, but one that allows them to move together. But the true mastery of these builders is revealed in what we cannot see. Within the very heart of the thickest fortress walls lies a hidden chamber of secrets, an internal architecture designed specifically to tame the earthquake's fury. At sites like the great fortress of Sacsayhuaman, the seemingly solid ramparts are in fact a brilliant deception. They are not single walls at all, but a sophisticated composite system known as double-wall construction. The process began with the erection of two independent parallel walls, each built with the same meticulous polygonal precision we have already explored. These outer shells were crafted to stand apart, leaving a deliberate gap, a void between them that could be several feet wide. This empty space was the crucial canvas for their next innovation. Into this cavity, workers would pour a carefully selected mix of loose rubble, broken stones, clay, and ordinary soil. This was not a haphazard dump of construction debris. It was a calculated fill, a granular core with a singular purpose. When the ground remains still, this inner fill simply sits there, an unremarkable mass of earth and rock. But when an earthquake strikes, this core transforms into the structure's dynamic heart. As the seismic waves pass through, the two outer polygonal walls begin their familiar, flexible dance, rocking and shifting minutely. This movement is transferred to the loose fill trapped between them. The countless small particles of stone and soil are forced to slide and tumble against one another, constantly rearranging in a chaotic, energy-absorbing ballet. The terrifying force of the tremor is not fighting against solid stone alone. It is being dissipated as friction and heat within this churning, granular medium. It is a monumental shock absorber built right into the fabric of the wall. The outer shells, themselves models of flexibility, act as containers for this damping core, preventing it from spilling out while allowing it to do its vital work. This creates a system of extraordinary resilience. A solid wall of the same immense thickness would transmit seismic energy directly through its mass, potentially developing catastrophic internal fractures. The double wall system, however, interrupts and diffuses that energy at multiple levels. The outer walls flex, the inner core churns, and together they absorb and neutralize shocks that would overwhelm a monolithic structure. It is a stunning anticipation of modern seismic damping technologies, where buildings are fitted with massive pendulums or fluid-filled pistons that counteract swaying. The ancient engineers achieved a similar effect using nothing more than earth, stone, and profound insight. They understood that to survive the Earth's violence, a structure must possess not just strength, but a kind of intelligent inertia, a capacity to swallow the shock and transform it into harmless motion. This hidden internal world, this secret chamber of shifting earth, stands as one of their most sophisticated answers to the perennial question of the Andes. High on a steep slope in the sacred valley, the fortress of Ollantaytambo is a living test of ancient seismic principles. This is not a ruin frozen in time, but a structure that faced a modern trial and proved its worth. Its builders chose a formidable site, a mountainside so sheer that constructing anything here seemed an act of defiance. The first and greatest challenge was the slope itself, a constant threat of gravitational slide made exponentially worse by earthquake shaking. To solve this, they began not with walls, but with a radical reshaping of the land. They cut deep into the mountainside, creating a series of massive, level terraces held in place by retaining walls of staggering scale. These are not mere garden steps, they are foundational platforms, each one acting as a unified raft to carry the structures above. The foundation stones for these terrace walls were set exceptionally deep, often keyed directly into the bedrock, creating an anchor that tied the entire complex to the most stable layer of the earth. This prevented the entire mountainside from behaving like a loose rug being shaken, instead turning it into a series of solid, interconnected shelves. Upon these engineered shelves, they erected walls from a beautiful, rose-colored stone called rhyolite. The stones are colossal, some weighing over 50 tons, yet they are fitted together with the same intricate, polygonal precision seen elsewhere. Here, the technique served a specific, slope-oriented purpose. During an earthquake, the primary danger on a hillside is not just back and forth shaking, but a downhill surge, a cascading collapse where one level fails and tumbles into the next. The interlocking puzzle of the polygonal masonry at Ollantaytambo was designed to counteract this exact threat. The complex joints between the stones force seismic energy to travel laterally, spreading out horizontally across the face of the terrace wall instead of channeling it downward in a destructive wave. Each terrace acts as an independent shock absorber, containing and dissipating the energy within its own level before it can amplify and crash into the terrace below. This design was not theoretical. It was proven in the middle of the 20th century. In the year 1950, a massive earthquake struck the Cusco region, leveling modern buildings of concrete and brick and causing severe damage to many colonial structures built atop older Inca foundations. Yet at Ollantaytambo, the ancient fortress temple stood with remarkable resilience. While some minor shifting occurred, there was no catastrophic collapse. The terrace system performed exactly as its designers intended centuries before. The deeply founded platforms held firm against slippage, and the interlocking stones in the walls redistributed the tremendous forces, allowing the entire complex to sway as a cohesive unit rather than shatter. Ollantaytambo is more than a monument. It is a case study written in stone, a demonstration that these were not just beautiful building methods, but a highly effective, field-tested technology for survival. The proof is in the quiet endurance of its walls, which faced the Earth's fury and simply settled back into place, a testament to a conversation with the land that began long before the first stone was ever set. Machu Picchu sits on a knife's edge, a breathtaking citadel suspended between two active geological faults. This is not a location chosen for ease of construction, but as the ultimate proving ground for an architectural philosophy. Every stone placed here was a deliberate answer to the land's volatile nature. The builders employed the full repertoire of seismic wisdom, from the foundational terraces that grip the steep slopes to the iconic polygonal walls and trapezoidal doorways that define its silhouette. Yet here they pushed their techniques even further. In a brilliant adaptation, many of the most important structures were not fused directly to the mountain itself. Instead, their foundations were carefully laid with a narrow, intentional gap separating the base of the wall from the solid bedrock below. This subtle space is a masterstroke of isolation. During an earthquake, the bedrock can lurch and roll with the seismic waves. A wall bonded rigidly to that moving platform would be forced to follow every violent jerk, risking fracture. But a wall resting upon it with a deliberate separation possesses a critical degree of independence. It can slide and shift slightly on its prepared bed, its movement dampened by friction, rather than being violently whipped by the bedrock's motion. It is a literal decoupling of the building from the Earth's most direct convulsions, a concept modern engineers replicate with expensive base isolators. The builders of Machu Picchu achieved it with a simple, profound understanding of space and motion. Nowhere is this philosophy more elegantly expressed than in the Temple of the Sun. This semicircular tower, built around a natural rock outcrop, features a curved wall of such precise, mortarless masonry that it appears to be a single, sculpted form. The stones fit together with that now familiar intricate puzzle work, but the curve adds another dimension of stability. An earthquake's force travels in waves, and a curved surface presents no flat plane for those waves to strike directly. The energy is deflected, guided along the wall's arc, and dissipated through the complex network of interlocking joints. This curved design, combined with the lack of mortar, allows the entire structure to flex and breathe as a cohesive shell. It does not fight the tremor, it embraces and redirects its energy. For centuries, this temple and the citadel around it have endured not just the periodic violence of earthquakes, but the relentless, soaking rainfall of the cloud forest. Water is the silent enemy of masonry, seeping into cracks, freezing and expanding. That the core structures stand so completely, with their joints still tight after centuries of this dual assault, is a quiet, powerful validation. It is proof that these were not just clever tricks, but a complete, integrated system for eternal endurance. The stones of Machu Picchu do not simply occupy a dramatic landscape, they converse with it, having learned the grammar of its tremors and the rhythm of its storms, speaking back in the timeless language of balance and resilience. The story does not begin with the Inca. They were the brilliant inheritors, the master refiners of a seismic wisdom forged over 1,000 years before their empire rose. To find the true origins of these earthquake-defying walls, we must look north to the shores of a vast, high-altitude lake and into the heart of a sprawling highland empire. Long before Cusco was a capital, other cultures were already holding conversations with the trembling earth. Around the immense, wind-swept waters of Lake Titicaca, the Tiwanaku culture flourished between 500 and 1000 AD. Their capital was a city of stone and ceremony, and its surviving architecture tells a clear story. They were pioneers of the precise stone fitting that would later define Inca masonry. At sites like the Calisasea compound, we see massive sandstone blocks, some weighing over 100 tons, cut into perfect rectangles and fitted together with seams so tight a razor blade cannot slip between them. This is ashlar masonry of an almost impossible standard, but they went even further. Archaeologists have found evidence that they used eye-shaped bronze clamps to join some of their largest stones together. These metal staples, poured molten into carved channels, acted like permanent stitches, holding the monumental blocks in a flexible metallic embrace that could withstand shifting and settling. This reveals a profound understanding. They knew that even perfectly cut stone needed an extra bond, a way to allow for movement without separation. They were engineering for permanence in a land that never stood still. Meanwhile, in the Central Highlands, the Wari Empire was building on a staggering scale. Theirs was not a culture of isolated temples, but of vast, planned administrative centers designed to control a rugged territory. At places like Picchu, near modern-day Cusco, they constructed immense cellular complexes, great grids of stone rooms and plazas that spread across the landscape. To build these urban centers on steep Andean slopes, they became masters of terracing. They sculpted mountainsides into colossal, level platforms, each one stabilized by formidable retaining walls. These were not just foundations for buildings, they were acts of geological control, creating stable ground where none naturally existed. Their walls, often built with a mix of rough fieldstone cores and finely finished exterior facades, show an early version of the composite construction techniques later refined at places like Sacsayhuaman. The Wari approach was about systematic reinforcement, about creating a unified, stable base from which to govern an unpredictable world. What we see across these earlier cultures is not a single, sudden invention, but a slow, cumulative technological tradition. The Tiwanaku perfected the intimate fit of stone to stone. The Wari mastered the large-scale engineering of the land itself. Each generation observed, experimented, and passed on hard-won knowledge. A tremor would topple a wall, and the builders would ask why, then adapt their next design. Over centuries, the core principles solidified: flexible masonry that could move, and deeply founded platforms that would not slide. This knowledge became part of the cultural fabric, a necessary wisdom for anyone who wished to build something meant to last. When the Inca emerged, they did not start from scratch. They stood on the shoulders of these seismic giants. They encountered the ruins of Tiwanaku and the sprawling terraces of Wari sites, absorbing the lessons etched into those stones. The Inca genius was in synthesis and perfection. They took the precise fitting of Tiwanaku and pushed it to an artistic extreme with polygonal shapes. They adopted the Wari terracing and scaled it to breathtaking proportions. They integrated these ideas into a unified architectural language that was both majestic and profoundly practical. To walk from a Wari complex to an Inca citadel is to witness the evolution of an idea, from a practical solution for survival into a soaring expression of power and harmony. The silent stones of Picchu and Tiwanaku are not separate mysteries. They are the earlier chapters in a very long story, the foundational paragraphs of a manual on how to build for eternity in a world that constantly tries to shake everything apart. This breathtaking precision was not the work of machines, but of human hands guided by generations of deep, tactile wisdom. The creation of these walls was a slow, deliberate art form, a process we might call the knitting of stone. It began with master masons, known in the Quechua language as Kolkapota Kamayok, the keepers of the stone. These were not merely foremen, but revered artisans who held the accumulated seismic knowledge of their culture. They could look at a raw, irregular boulder and see within it the exact shape needed to complete a section of the living puzzle. Under their direction, teams of workers would undertake a process of profound patience. Using hammerstones made of even harder rock, they would begin to peck away at the granite or andesite, not to carve a predetermined shape, but to find the shape hidden within. It was a conversation with the material, a gradual revealing. Once a stone was roughly shaped, the true test began. Workers would lift it using ramps and ropes and attempt to place it into the growing wall. It would not fit, of course, so they would lower it, examine the contact points, and the masons would instruct where to remove just a little more material. This cycle of test fitting and adjustment would be repeated dozens, perhaps hundreds of times for a single stone. The final act was one of intimate refinement. They would use sand and water as a natural abrasive, grinding two stones together in a slow, rocking motion. Over hours, the surfaces would wear into perfect complementary curves, creating that signature friction-locking fit. This hands-on, iterative process did more than shape stone, it shaped understanding. A master mason developed a feel for the material, an intuition for how a particular grain or fissure would respond to pressure and movement. He knew through his fingertips how that stone would behave when the earth began to tremble. This immense body of knowledge, this library of engineering intuition, was not written down in manuals. It was transmitted orally and through lifelong apprenticeship, a young worker learning by watching, by doing, by feeling the stone himself. It was a living tradition, passed from one generation of hands to the next. The profound loss that followed the events of the 16th century was not just one of political power, but of this irreplaceable cognitive library. The master masons, their apprenticeship shattered, took the deepest secrets of the stone knitting art with them. We are left with the magnificent results, but the fluent, tactile language in which they were composed fell silent, leaving us to reverse engineer the grammar of their resilience from the awe-inspiring text of the walls themselves. Water was their silent adversary, a patient force that could unravel even the strongest wall from within. The Andean builders understood that seismic resilience was not just about surviving the violent shaking, but about outlasting the quiet, daily siege of rain and groundwater. Their mastery extended far beyond stone fitting, into a profound understanding of hydrology, the science of water movement. They recognized a terrifying phenomenon that modern engineers still fear: soil liquefaction. When loose, saturated soil is shaken violently, the water pressure between the grains increases so dramatically that the solid ground can momentarily behave like a liquid, losing all strength to support anything built upon it. An entire fortress could sink or tilt catastrophically, not from the shaking itself, but from the ground turning to soup beneath it. To prevent this, they engineered their structures to stay perpetually dry, integrating drainage not as an afterthought, but as a core component of seismic defense. Look closely at the base of many ancient retaining walls and terraces. You will often find a deliberate gap, a small channel or a row of stones slightly set back. These are not construction errors but carefully designed weep holes. Their purpose is to allow any water that percolates through the wall or accumulates behind it to escape freely, relieving the hydraulic pressure that could build up and push the masonry outward. It is a simple, brilliant pressure release valve carved in stone. The real ingenuity, however, lies beneath the surface, hidden from view. The massive terraces that sculpt the mountainsides are far more than just level platforms. They are sophisticated, layered drainage systems. Builders would first lay down a deep bed of large, angular stones. On top of this, they placed a layer of smaller gravel, followed by a layer of coarse sand, and finally the rich topsoil for agriculture. This inverted filter acts like a giant sponge and conduit. When the heavy rains come, water soaks through the topsoil but is immediately captured by the sand and gravel layers. Instead of pooling and saturating the ground, it is channeled sideways through this permeable mattress, flowing out through the weep holes in the terrace walls. This keeps the foundational soil beneath the entire complex stable and relatively dry, its grains firmly locked together, resistant to liquefaction when the next tremor arrives. Nowhere is this hydrological harmony more elegantly displayed than at Machu Picchu. The citadel is a masterpiece of water management, an intricate network of stone canals fed by a natural spring on the mountainside runs through the entire site. This system was not merely for drinking or ceremonial use, it was for hydraulic control. The canals meticulously collect and redirect the torrential runoff from the mountain slopes above, preventing it from cascading over the buildings and terraces. The water is guided along predetermined paths and safely discharged down the steep hillsides. Every courtyard, every staircase has subtle slopes and channels to direct rainfall away. By mastering the flow of water, the engineers removed a primary trigger for disaster. They ensured that when the earth shook, the ground beneath their walls would remain a solid, dependable partner, not a treacherous fluid. This holistic vision, where seismic stability and hydrological control are two sides of the same coin, reveals a depth of environmental engineering that we are only now fully appreciating. They did not fight the mountain's water, they invited it in, gave it a clear path to follow, and in doing so, tamed one of nature's most destructive collaborative forces. Perhaps the most elegant explanation lies not in resisting force, but in harmonizing with it. Beyond the visible geometry and hidden drains, a deeper, more subtle layer of genius may be at work within these walls, one that speaks the language of vibration itself. Some researchers propose a fascinating theory that these structures were unconsciously engineered as massive, passive tuning forks for the Earth's tremors. This idea centers on the concept of sympathetic vibration or tuned mass damping. In simple terms, every object has a natural frequency at which it prefers to vibrate, like a specific note on a piano. If you strike that note while holding a tuning fork of the same pitch nearby, the fork will begin to hum in sympathy, absorbing energy from the sound wave. Now, imagine that principle scaled up to the size of a fortress. The seismic waves traveling through the Andean bedrock have their own distinct frequencies, patterns of shaking that repeat based on the geology of the region. The theory suggests that the ancient builders, through endless cycles of trial and observation, may have arrived at designs that inadvertently tuned their walls to these very frequencies. How would this work in practice? Consider the internal chaos of a double wall's rubble core. That loose fill of stones and earth is not a single mass, but a collection of countless individual particles. When a seismic wave of a particular frequency hits, it sets this granular interior into a churning, tumbling dance. The energy of the wave is not just passing through, it is being actively captured and consumed by the movement of the rubble, as each collision between particles converts a tiny bit of the earthquake's destructive kinetic energy into harmless heat and sound. The wall, in essence, begins to hum with the tremor, but that hum is safely trapped and dissipated within its granular heart. This effect would be amplified by the very fabric of the masonry itself. The polygonal stones, with their myriad of angled contact points, create a complex network of tiny interfaces. As the wall sways, these countless surfaces grind and slip against each other with microscopic movements. This friction acts as a continuous, distributed brake, transforming the large, terrifying motion of the quake into a gentle, internal warmth. It is a brilliant, maintenance-free damping system that operates on the same principle as the shock absorbers in your car, but built entirely from stone and soil, designed by generations of keen observation. This is not magic, but physics harnessed through profound intuition. They were designing with the natural forces, not against them, creating structures that could absorb the Earth's song and transform its most violent notes into a harmless, dissipating whisper. This leads us to a pivotal moment of cultural and technological rupture, when this deep, accumulated wisdom faced an existential threat not from nature but from human conquest. The story of seismic design is a global conversation, spoken in different architectural languages. To fully appreciate the Andean voice, we must listen to how other ancient cultures answered the same trembling question. The Romans, master builders of an empire, confronted earthquakes with a philosophy of immense, unified strength. Their signature material was a revolutionary hydraulic cement called pozzolana, a mix of volcanic ash and lime that could harden even underwater into a concrete of legendary durability. With this material, they constructed vast vaults, domes, and rigid wall systems. Their strategy was to create monolithic structures so massive and coherent that they could absorb and distribute seismic forces through their sheer bulk and the limited tensile strength of their concrete and brickwork. Think of the Roman approach as a powerful, muscular wrestler, bracing himself solidly to withstand a series of blows. The structure itself was the shock absorber, and its survival depended on the material not cracking under the incredible bending and shearing stresses. This worked brilliantly for many centuries, but it was a solution rooted in material science and mass, a testament to Roman engineering might. On the other side of the world, in the earthquake-prone islands of Japan, an entirely different language of resilience evolved. Traditional Japanese wooden architecture, seen in pagodas and temples, is a study in elegant flexibility. Builders used complex, interlocking wooden joinery without nails or rigid glue, creating frames that could sway and rock. Heavy tile roofs acted as stabilizing masses, while the walls themselves were often non-structural sliding panels that could move independently. This system is like a graceful willow tree in a storm, its branches and leaves flowing with the wind, its deep roots allowing it to bend and return. The Japanese solution embraced lightweight, flexibility, and deliberate, controlled movement. Now, place the Andean technique between these two globally celebrated models. It defies easy categorization. The Andean builders created structures of colossal weight, rivaling Roman monuments in their sense of permanence and mass. Yet they achieved a flexibility that seems to belong to the wooden world of Japan. Their genius was in synthesizing these seemingly opposite principles into a third, unique path. They used immense weight not as a rigid brace but as a dynamic tool. The thousands of tons of stone in a fortress wall were not fused into a single brittle shell. Instead, that weight was cleverly distributed across a geometric mosaic, where each stone's mass contributed to the frictional lock holding the assembly together. Unlike Roman concrete, which could fail in tension from bending, the polygonal walls had no mortar to crack. The forces were always compressive, pushing stone against stone, a load the material handles perfectly. And unlike the lightweight Japanese frame, which sways freely, the Andean wall's movement was minute, a complex internal redistribution within a seemingly solid form. It was flexibility through granularity, movement through micro-shifting, and stability through intelligent confinement. This comparison reveals a profound truth about human innovation. Faced with the universal threat of earthquakes, cultures in complete isolation arrived at brilliant, yet fundamentally different, solutions. The Romans trusted chemistry and mass. The Japanese mastered joinery and flexibility. The Andeans, however, spoke in the pure geometry of stone, unlocking a secret where weight and movement were not enemies, but partners in an eternal dance. Their solution was not just effective, It was a breathtaking inversion of expectation, proving that the heaviest materials could be taught to be the most resilient dancers. The stones have whispered their secrets for centuries, and now modern science is finally learning their language. Using sophisticated computer modeling and advanced seismic analysis, contemporary engineers are quantifying what the ancient builders knew intuitively. They create digital twins of these walls, subjecting them to virtual earthquakes that mimic the violent forces of the Andean fault lines. The results of these simulations are not just confirmations, they are revelations. The intricate polygonal joints, for instance, behave exactly as modern engineers hope critical connections will in a tremor. They act as what are called plastic hinges. In a steel-framed building, a plastic hinge is a specially designed section of a beam that is meant to bend and deform under extreme stress, absorbing energy without snapping. This controlled yielding prevents a sudden, brittle collapse. Astonishingly, the computer models show that the ancient stone joints perform a nearly identical function. Each angled interface between two massive stones allows for a tiny amount of rotation and slippage. This micro-movement is the wall's way of bending, of safely yielding to the force, and it does so without losing its overall structural integrity. It is a built-in flexibility, a ductility carved in granite that modern codes strive to achieve with carefully engineered steel and concrete. The simulations also provide hard numbers for the wall's legendary stability. That subtle inward tilt, the batter, is shown to dramatically lower the structure's center of mass. When the digital quake hits, the model calculates the overturning forces trying to push the wall over. The inclined design consistently shows a factor of safety several times higher than a perfectly vertical wall of the same height and weight. It mathematically proves the wisdom of the slope, showing how gravity itself becomes an ally during the shaking, driving the stones into a tighter, more stable configuration. Perhaps the most significant finding from these high-tech studies concerns energy dissipation. Engineers measure this with a value called the damping ratio. It describes how quickly a structure can absorb and neutralize vibrational energy. A high damping ratio is the holy grail in seismic design. It means the building stops shaking quickly after the main tremor passes, preventing prolonged destructive swaying. The analysis of these ancient, mortarless walls reveals a damping ratio that is remarkably high, often comparable to or even exceeding that of some modern structures with added dampers. The reason lies in the dry stack construction itself. All those countless points of friction between the stones, that gentle grinding of granite on granite, acts as a massive, distributed energy sink. The terrifying kinetic energy of the earthquake is not stored in the wall, waiting to cause more damage. It is converted into harmless heat and sound across millions of microscopic contact points almost as fast as it arrives. This rigorous quantitative validation is profound. It demonstrates that the empirical knowledge painstakingly gathered over generations aligns perfectly with modern principles of seismic engineering, ductility, energy dissipation, and structural redundancy. The builders did not have the equations, but they understood the relationships those equations describe. They knew that a structure must be able to yield, to absorb a blow, and to have multiple ways to carry a load if one path fails. Modern science is not discovering something new in these walls. It is finally providing the mathematical proof for an ancient, silent intelligence. It is a powerful convergence where cutting-edge computational tools meet timeless craftsmanship, and both point to the same elegant truth about how to stand firm in a moving world. This validation from the realm of supercomputers and sensors forces us to ask a deeper, more unsettling question about the trajectory of knowledge itself. Yet the very ground that tested these walls would soon witness a far more destructive tremor, one of cultural and technological rupture. The arrival of Spanish colonizers in the 16th century did more than topple an empire. It severed a 1,000-year conversation with the earth. The seismic wisdom encoded in polygonal stone was not just ignored, it was actively discarded as primitive, replaced by European building traditions utterly unsuited to the Andean reality. Colonial architects and engineers brought with them the aesthetics and techniques of the Renaissance and Baroque, favoring straight lines, right angles, and the widespread use of lime mortar to bind neatly cut rectangular stones or bricks. To them, this represented progress, civilization, and the triumph of their own technological order. But in the volatile geology of the Andes, this imported architecture held a fatal flaw, a profound rigidity. Where the ancient walls were designed to flex and dissipate energy, these new structures sought to be monolithic and unyielding. The lime mortar, while strong in compression, was brittle. When the inevitable earthquake struck, these rigid frames could not accommodate the complex, rolling motions of the ground. The mortar would crack and powder, the straight lines of the masonry would become fracture lines, and the entire building, often top-heavy with elaborate bell towers and vaulted ceilings, would collapse in a heap of rubble. The historical record is filled with tragic repetition. Magnificent cathedrals and churches, like the original basilica in Cusco, were completed with great celebration, only to be shattered by a major tremor decades or even years later. The response was seldom to question the building method itself, but to rebuild on the same vulnerable plan, often using stones quarried from the very Inca structures that had survived the same quake intact. This cycle of construction and catastrophic collapse highlights a devastating disconnect, the willful abandonment of localized, time-tested knowledge in favor of an imported ideal. The cost was measured not just in shattered stone, but in immense loss of life, cultural heritage, and continuous, wasteful labor. The most poignant symbol of this disconnect stands quietly in city plazas across the Andes. It is the common sight of a Spanish colonial church or palace, its walls cracked and patched, built directly upon a foundation of flawless, interlocking Inca masonry. The visual contrast is stark, a lesson in humility written in stone. The smooth, irregular polygonal blocks below sit unmoved, having absorbed centuries of tremors, while the mortared, rectangular stones above show clear scars of repair and reinforcement. The ancient wall does not simply support the colonial structure, it silently judges it, a testament to the fact that in this specific, violent dialogue with the planet, the older language was the more fluent one. This period stands as a sobering case study in the perils of technological arrogance, showing that innovation is not always about adopting the newest method, but about deeply understanding the problem you are trying to solve. The surviving Inca stones, holding up the very architecture that sought to erase them, ask a persistent question of all who build: will you listen to the land, or will you impose your will upon it until it shakes you off? The 20th century brought a series of violent tremors that served as the ultimate, unplanned laboratory. In the year 1950, a massive earthquake struck the heart of the Cusco region, its force leveling entire neighborhoods of modern concrete and brick. Colonial churches, their rigid towers and mortared walls unable to flex, crumbled into clouds of dust. Yet from that chaos emerged a startling, silent testimony. Amid the ruins, the ancient Inca foundations and polygonal walls, often serving as the base for those very colonial structures, remained standing. They had settled, shifted slightly, but they had not shattered. This pattern repeated in later quakes, each tremor delivering the same verdict. The earth itself was conducting a brutal comparative test, and the results were undeniable. The old stones, built through a forgotten dialogue with the land, consistently outperformed the imported architecture of centuries later. This was not a matter of luck, but of design. These seismic events did more than shake the ground. They shook the modern understanding of engineering history. They sparked a fundamental question among archaeologists and engineers. If our strongest modern materials failed where ancient stone succeeded, What crucial knowledge had been lost in the intervening centuries? This question launched a new era of study, moving beyond admiration of the ruins to a rigorous analysis of their hidden mechanics. Pioneering figures like the Peruvian engineer Santiago Agurto Calvo dedicated themselves to this forensic investigation. He and others began to systematically measure, map, and model the walls. They documented the precise angles of the stone joints, calculated the effects of the inward batter, and theorized about the energy dissipation within the dry stack construction. Their work shifted the perspective from viewing these sites as static archaeological artifacts to understanding them as dynamic, functioning machines for seismic survival. This renewed insight has profoundly changed how we approach preservation today. The old conservation model, born in a different climate, often involved repointing crumbling joints with hard, rigid cement mortar. This was done with the best intentions to strengthen and stabilize, but we now understand that such intervention is often a form of architectural sabotage. Smothering those meticulously carved joints in cement destroys their very purpose. It locks the stones into a brittle embrace, preventing the micro-movements and friction that are the wall's primary defense. Modern preservation philosophy, informed by this hard-won engineering insight, advocates for minimal intervention. The goal is to protect the integrity of the original system. This often means simply clearing vegetation and controlling drainage, or in cases where stabilization is absolutely necessary, using soft, flexible mortars that mimic the properties of the original earth, or even using discrete, reversible supports that do not inhibit the structure's natural ability to move. It is a humble shift, a recognition that the greatest act of care we can offer these monuments is not to fix them according to our standards, but to first listen to the profound intelligence already built into every stone. We are learning to conserve not just the form, but the function, preserving the ancient conversation between the wall and the world it was designed to navigate. These ancient principles are no longer locked in the past. They are actively reshaping the future of how we build. The same seismic wisdom that preserved Machu Picchu is now inspiring a new generation of engineers who are translating Stone Age insights into cutting-edge technologies for our cities. One of the most direct applications lies in the concept of controlled friction, the very force that holds those polygonal walls together. Modern researchers are studying what they call sliding interfaces, designing special joints and bearings that allow parts of a building to move independently during a quake. These are not rigid welds, but carefully engineered connections that permit a safe, measured amount of slippage, converting destructive force into harmless friction, just like the grinding of ancient granite. This idea is central to base isolation systems, where a building is essentially placed on a layer of flexible pads or sliders. During an earthquake, the ground lurches beneath, but the isolated structure above moves more slowly and smoothly, dramatically reducing the shaking felt inside. It is a high-tech echo of the Inca strategy, decoupling the building from the worst of the Earth's convulsions, just as their walls were subtly separated from the bedrock. The hidden rubble core within those double walls is finding its modern counterpart as well. The concept of using loose, granular materials for energy dissipation is leading to innovative designs for seismic barriers. Engineers are experimenting with trenches filled with gravel or recycled tire shreds placed around the foundations of critical infrastructure, like bridges or power plants. When seismic waves hit this granular zone, the energy is scattered and absorbed as the particles shift and tumble, protecting the structure behind it. It is a deliberate recreation of that internal, churning dance, scaled up to shield our most vital modern networks. Perhaps the most profound lesson, however, is not a specific technique, but an entire philosophy of design. For decades, the goal of seismic engineering was simply to prevent collapse, a life safety standard. The ancient walls teach a higher standard. Modern codes are now embracing performance-based design. This philosophy asks not just will the building stand, but how will it perform? Can it be designed to sustain only repairable damage? Can it be operational again quickly after a major event? This shifts the focus from sheer resistance to resilience, designing structures with a built-in capacity for controlled, non-destructive movement. It accepts that a building, like those ancient walls, must have a way to yield, to absorb the blow, and to settle back into a usable state. The stones teach us to work with an earthquake's energy, to invite it in and safely guide it away, rather than to stand rigidly and risk being broken. This timeless lesson is becoming the cornerstone for building the resilient cities of tomorrow, proving that some of our most advanced ideas have roots that reach deep into the wisdom of a forgotten stone. This ancient knowledge is not a museum piece, but a living blueprint for a more resilient future. In regions of the world where seismic risk is a daily reality and economic resources are scarce, the Andean principles offer a powerful alternative to expensive, imported building methods. They point toward a path of sustainable vernacular architecture, where safety is built from the ground up with the very materials underfoot. Imagine a community in a high-risk zone, where the cost of steel and concrete is prohibitive, and imported designs are often ill-suited to the local climate and culture. Here, the lessons of the polygonal wall become profoundly practical. A simplified version of the technique, focusing on the core ideas rather than artistic perfection, can be transformative. Builders can be trained to shape local stone into interlocking blocks, emphasizing that crucial trapezoidal shape for openings and a gentle inward lean for walls. The most critical investment is not in material but in time and knowledge, ensuring a deeply prepared, well-drained foundation. This approach uses what is abundantly available, local stone and local labor, turning a community into its own best defense. It dramatically reduces the need for carbon-intensive materials that must be transported over long distances, making it not only affordable but also environmentally thoughtful. This is resilience that is culturally grounded and technologically appropriate, a fusion of ancient insight and modern need. It empowers people to build their own safety using the landscape around them, creating homes and schools that are woven into the very fabric of their place. In a world facing both increasing seismic activity and the urgent need for sustainable development, these low-tech, high-wisdom solutions are more relevant than ever. They remind us that sometimes the most advanced path forward is to rediscover the profound intelligence already written in the stone. The seamless fit of the stones may have served a purpose far beyond the physical. For the Inca and the cultures before them, the world was not divided into separate realms of engineering and spirit, but was a single, interconnected whole. Their cosmology described a universe in delicate balance, with the human world, Pacha, existing between the upper world of the gods, Honan Pacha, and the inner world of the ancestors and origins, Uku Pacha. In this view, a perfectly built wall was more than a feat of construction. It was a sacred act of alignment, the meticulous joining of stone to stone, where not even a blade of light could pass, might have been seen as a microcosm of the ideal cosmic order. It mirrored the harmonious fit between the earthly realm and the divine, a physical prayer for stability in a universe they knew was fundamentally in motion. The wall, in its flawless geometry, became a conduit, a place where the human world could touch the perfection of the spiritual one. This transforms our understanding of the mason's labor. Each hammer stroke to shape a curve, each hour spent grinding two stones into perfect complement, was not just technical work. It was an act of devotion, a ritual performed to please the very forces of the earth they sought to withstand. The primary deity in this relationship was Pachamama, the Earth Mother, a living, conscious being who provided sustenance but could also unleash terrible fury through earthquakes and landslides. Building in a way that danced with her tremors rather than defying them was a form of profound reverence, A wall that could sway and settle without crumbling was not just smart engineering, it was a sign of Pachamama's acceptance, a visible manifestation of her favor. The structure's endurance proved that the builders had listened to her language and responded with respect. This spiritual dimension gave the walls an immense political power. The Inca state was a theocracy where the emperor, the Sapa Inca, was considered the son of the sun god in Thai. His authority was divinely ordained. The construction of earthquake-resistant fortresses, temples, and storehouses across the empire served a dual purpose. Functionally, they secured grain, housed armies, and impressed subjects. Symbolically, they were stone proclamations of the empire's eternal stability, a divine mandate made literal. They demonstrated that the Inca, through their sacred knowledge and favor with the gods, could achieve what seemed impossible, creating permanent order in a land of chaos. A subject seeing the immense, unmoving walls of Sacsayhuaman would understand a clear message. The empire was as enduring as these stones, and its rulers were in harmony with the powers of the cosmos. This fusion of the practical and the spiritual is what elevates the technique from mere craft to a cultural masterpiece. The walls were a physical prayer for permanence, a dialogue with the divine written in the grammar of seismic survival. Every perfectly fitted joint was both an engineering solution and a spiritual statement, declaring that in a trembling world, humanity could still find a way to build something that felt, and perhaps even was, eternal. The silent stones still hold mysteries no eye can see. While we grasp the broad principles of their seismic dance, the precise choreography of their creation remains partially veiled. How, for instance, did builders manage the Herculean task of transporting stones weighing 50 tons or more across rugged mountain terrain, and then engage in that painstaking cycle of test, fitting, and adjustment? Common explanation involves ramps, ropes, and large teams of laborers, and while that is certainly part of the story, the logistical precision required to execute this on the scale of an Ollantaytambo or Sacsayhuaman is staggering. It leads to compelling questions about planning. Did master masons work from detailed scale models carved in clay or stone, plotting out the complex three-dimensional puzzle in miniature before a single granite block was quarried? Or was the design more organic, emerging from the master's mind and the unique shape of each stone as it arrived on site, a real-time composition guided by deep intuition? Some researchers even explore more esoteric possibilities, like the potential acoustic properties of the walls. Could specific resonant frequencies created by striking the stones have been used to assess their fit or density during construction, or to enhance ceremonial practices that sought harmony with the Earth's own vibrations? These are not just historical curiosities, they are active frontiers of investigation. Today, archaeologists and engineers are employing tools the original builders could never have envisioned to read these stone libraries at a new resolution. Three-dimensional laser scanners and drones equipped with high-resolution cameras perform photogrammetry, capturing millions of data points to create ultra-precise digital models of entire walls. These virtual replicas allow scientists to analyze patterns of stone placement, joint angles, and weight distribution with a mathematical eye, searching for repeating algorithms or geometric rules that are invisible to human observation. This digital archaeology can reveal the hidden syntax of the walls, the underlying grammar that governed which stone shape went where. It might uncover that what looks like artistic randomness is, in fact, a highly optimized pattern for load-bearing and energy dispersal, a formula for resilience passed down through generations of hands-on work. Each scan, each new data set, is like turning a page in a vast, unbound engineering manual. We are slowly learning to read it, and with every technological advance, from ground-penetrating radar to artificial intelligence pattern recognition, we get closer to a complete translation. The promise is that one day we may not just admire these walls, but fully comprehend the entire seismic codex they represent, unlocking every subtle instruction for how to build something that can truly listen to the earth. But the stones hold more than engineering secrets, they hold memory and meaning. To truly understand these walls, we must listen to more than the echoes of ancient tremors. We must hear the living voices of the people for whom these sites are not ruins but sacred ancestors. The fortress of Sacsayhuaman is not merely a seismic marvel. It is a place of profound spiritual significance, a site of ceremony and connection for descendant communities. This creates a vital ethical dimension for anyone who seeks to study or preserve this heritage. The pursuit of knowledge here cannot be a one-sided extraction. It must be a respectful dialogue. Imagine the difference between a researcher arriving with a scanner to take measurements from a wall, and that same researcher sitting first with community elders, listening to stories of the place, understanding its role in the cosmology of the living culture. The technical data gathered might be identical, but the context, the meaning, is transformed. The wall is no longer just a static object of analysis, it becomes a participant in an ongoing story. This collaborative approach, which brings together archaeologists, structural engineers, and indigenous knowledge holders, leads to richer, more holistic understanding. An engineer might see a trapezoidal doorway and calculate its load distributing angles. A knowledge holder might share that the shape represents the layered cosmos, a portal between worlds. Both perspectives are true, and together they reveal the full genius of the design, a fusion of physical necessity and spiritual vision. This partnership also guides crucial preservation decisions. The pressure to make these sites more accessible for tourism is immense. The easy path might involve pouring concrete supports or building wide staircases that alter the original landscape. But a collaborative, ethically informed approach asks a different question. How do we protect the integrity of this place while honoring its sacred nature? The answer often lies in minimal, reversible interventions, controlling visitor flow to prevent erosion, and using traditional materials and methods for any necessary repairs. It means sometimes choosing to limit access to the most fragile areas, prioritizing the site's long-term health and cultural sanctity over short-term convenience. This is not about locking the past away, but about stewarding it with reverence. The story of these earthquake-resistant walls is at its heart a profoundly human story of observation, adaptation, and creative genius in the face of immense challenge. To share that story responsibly is to do more than recite facts about stone fitting. It means consistently honoring the cultural and spiritual context from which this technology emerged. It requires acknowledging that this wisdom belongs to a living tradition, not a vanished civilization. When we present these sites, we have a choice. We can frame them as mysterious achievements of a lost people, or we can present them as enduring legacies of ancestral knowledge that continues to inform and inspire their descendants today. The latter approach does not diminish the wonder, it deepens it. It ensures that the pursuit of knowledge about these ancient stones becomes a bridge that strengthens cultural pride and continuity, rather than an act that appropriates or silences the very culture that created them. In the end, the greatest lesson these walls teach might not be about physics, but about perspective, reminding us that the most resilient structures are always those built on a foundation of respect. This monumental dialogue between human ingenuity and planetary force leaves us with more than ruins. It offers a new lens for seeing our own world. The polygonal puzzles of Sacsayhuaman, the terraced heights of Machu Picchu, they all whisper the same counterintuitive truth. True resilience does not come from rigid defiance, but from intelligent flexibility, from a precision that allows for movement, and from a partnership with the environment rather than a conquest of it. These walls stand as a quiet rebuke to any assumption that older technology was primitive. They were, in fact, exquisitely advanced within their context, solving a problem with an elegance that modern engineering is only now fully quantifying. Their legacy challenges a linear view of progress, suggesting that wisdom can be lost as well as gained, and that some solutions are so perfectly attuned to their place and purpose that they remain unsurpassed. In an era defined by global instability, from climate volatility to the literal shaking of our urban foundations, these stones offer more than historical curiosity. They provide a profound philosophical blueprint. They teach us that sustainability is not just about the materials we use, but about the relationships we design. A sustainable future, like a stable wall, must be built on principles of adaptation, of distributed strength, and of systems that can absorb shock without breaking. It asks us to observe the natural forces at play, to learn their patterns, and to design our lives and cities in harmony with them, not in a futile battle against them. The silent stones of the Andes do not boast of their endurance, they simply demonstrate it. They remind us that the most enduring solutions are often born from humility, from a deep listening to the world, and from the patience to fit each piece into a coherent, resilient whole. Their legacy is carved not just in rock, but in a timeless wisdom, waiting for any generation willing to learn the language of balance.